Imagine a machine launched from Earth almost half a century ago, now more than 25 billion kilometers away. There is no atmosphere around it. No wind. No sound waves traveling through air. And yet, this ancient spacecraft is detecting something that scientists can transform into sounds we can actually hear. The source of some of those signals began with our own sun. A violent eruption on the sun sent a shock wave racing outward through the solar system. After traveling billions of kilometers, that disturbance eventually reached the outer boundary of the sun's influence and interacted with the extremely thin plasma between the stars. Voyager 1 detected the resulting vibrations. It was almost as if the space around the spacecraft had been struck like the surface of a giant bell. And that is only the beginning of the story. Voyager 1 launched on September 5, 1977, from Cape Canaveral, Florida. At the time, its engineers were building a spacecraft designed primarily to explore the outer planets. Nobody could know that decades later, the same machine would still be operating far beyond the planets and collecting measurements from interstellar space. The spacecraft passed Jupiter in 1979 and Saturn in 1980. Those encounters transformed our understanding of the giant planets and their moons. Voyager captured images that revealed details never seen up close before. But after Saturn, Voyager 1 continued outward. It crossed beyond the orbits of the planets and entered the enormous region dominated by the Sun's solar wind and magnetic field. Then came August 25, 2012. At roughly 121 astronomical units from the Sun, Voyager 1 crossed the heliopause, the boundary separating the solar system's heliosphere from the surrounding interstellar environment. That made it the first spacecraft ever confirmed to enter interstellar space. Today, Voyager 1 is vastly farther away. Its distance from Earth is so enormous that a radio signal traveling at the speed of light needs more than 23 hours to make the journey in one direction. Think about that. When engineers send a command, they cannot immediately see whether it worked. The spacecraft is so far away that communication itself becomes a conversation stretched across almost 2 days. And Voyager is still listening. What does Voyager actually hear? Voyager 1 carries an instrument called the plasma wave system. It was not designed to record music. It does not contain a microphone. Instead, the instrument detects electrical fluctuations created by plasma surrounding the spacecraft. Plasma is a state of matter made up of charged particles. Interstellar space may look completely empty, but it is not truly empty. Even between stars, incredibly thin clouds of ionized material are spread throughout the galaxy. When electrons in that plasma oscillate, they create changes in electric fields. Voyager's long antenna system can detect those tiny variations. Scientists can then convert the measured frequencies into audio frequencies that humans can hear. So when you hear a Voyager sound, you are not hearing air moving around the spacecraft. You are hearing a translation of real measurements made in space. The frequency is especially useful because it tells scientists something about the plasma itself. In general, a higher plasma wave frequency corresponds to a higher concentration of electrons around Voyager. That means the instrument can effectively act as a remote probe of the environment through which the spacecraft is traveling. And this becomes especially interesting when Voyager encounters disturbances created by the Sun. The Sun can send waves across the solar system. Our Sun looks peaceful from Earth, but it is an extremely active star. It constantly releases charged particles through the solar wind. Occasionally, however, the Sun produces much more violent events. One of these is called a coronal mass ejection, or CME. During this CME, an enormous amount of magnetized plasma can be expelled from the Sun and launched outward at tremendous speeds. Some solar eruptions reach Earth within days. But the disturbance does not simply stop at Earth, it continues moving outward. As these disturbances travel through the solar system, they interact with the solar wind and eventually with the environment surrounding the heliosphere. When a powerful shock wave reaches the interstellar plasma near Voyager, it can cause the electrons in that plasma to oscillate. And Voyager can detect those oscillations. Scientists sometimes compare the process to striking a bell. The shock wave provides the disturbance. The interstellar plasma responds. Voyager's instrument detects the resulting electrical vibration. That is how an event that began on the surface of the Sun can eventually produce a measurable signal billions of kilometers away. The first interstellar shock signals soon after Voyager 1 crossed the heliopause, the spacecraft detected one of these remarkable events. In late 2012, a disturbance associated with solar activity reached Voyager's location and caused the surrounding plasma to oscillate strongly enough for the plasma wave system to detect it. The measurements provided important evidence about the environment Voyager had entered. The plasma outside the heliosphere was considerably denser than the solar wind plasma Voyager had previously been traveling through. Another major event followed in 2013. Then another began in 2014. These events gave scientists rare opportunities to measure the interstellar environment directly. And Voyager's position made those measurements extraordinarily valuable. Earth-based telescopes can observe distant objects across enormous distances. But Voyager was physically traveling through the environment scientists wanted to understand. It was not looking at interstellar space from millions of kilometers away. It was actually there. That distinction matters. A spacecraft with almost no power left there is another incredible part of this story. Voyager 1's transmitter produces only a tiny amount of power by modern standards, roughly comparable to the power used by a small household light bulb. Yet that incredibly weak signal must travel across more than 25 billion kilometers before reaching Earth. By the time the transmission arrives, it is extraordinarily faint. NASA relies on the Deep Space Network to receive it. Huge radio antennas in California, Spain, and Australia work together to maintain communication with distant spacecraft. Some of these dishes are approximately 70 meters across. Even with antennas that enormous, Voyager's communication rate is extremely slow compared with anything we use today. Its data arrives at only a tiny fraction of modern internet speeds. But every bit matters. Those bits contain measurements collected from a region of space where humanity has almost no other instruments. And that is why Voyager's aging technology remains scientifically valuable. Then scientists found something unexpected for years. Voyager's strongest plasma signals were associated with major shockwave events. Scientists could use these events to estimate the density of the interstellar plasma. But there were long periods when nothing dramatic happened. Then researchers went back through archived Voyager data. They discovered something hiding beneath the stronger signals. A faint, persistent tone. It was not a giant burst. It was not a dramatic solar shock. It was a weak, narrow-band signal that appeared to continue between major events. In other words, Voyager was detecting something that seemed to be part of the natural background environment of interstellar space. Scientists began describing it as a persistent plasma hum. This discovery was important because it changed what Voyager could tell researchers about the space between stars. Instead of obtaining an occasional measurement only when a powerful solar disturbance arrived, scientists could potentially use the faint background signal to track changes in plasma density over much longer periods. That is like the difference between taking one photograph every year and recording a continuous video. And the continuous record revealed something else. The interstellar plasma was not perfectly smooth. Its density changed. There were fluctuations occurring across surprisingly large distances. Those variations provided evidence that the plasma between stars is much more dynamic than the simplest models might suggest. The region Voyager is traveling through contains structure, waves and turbulence. The space between stars is not an absolutely empty, silent void. It has its own physical environment. And Voyager 1 is moving through